That's 3. That's 3. That's 3. Oh, can you see it? Oh, you can see it. It's not. Right there.
How much are you using?
3.
Did you get 3 grams?
3.7. 3.07.
3 grams. Now, the mixing should be done in a beaker, not in the graduated cylinder. So you have a beaker on your desk right there. So you want to mix it in the beaker.
So you want me to pour it in there?
Yes.
Yeah, where did that green come from?
Now pour the liquid back into the graduated cylinder so you can get the rest of that out of there.
What?
Pour this back in here and rinse it just a little bit so you can get all of the solid into your beaker. That's probably good right there. And then rinse it. Pour it back in. Harley, you're doing fantastic. Need some help?
I know. Yeah. You don't know how to make the beaker. Yeah.
You're going to put 25 milliliters of the water in the beaker.
25.
Yeah, it's just staying in the same spot.
Now it's going to raise as you add the aluminum. So you're getting the initial temperature, so write down what the initial temperature is.
On which side, the 20 or the 60?
You can go with Celsius. Carbide, in the presence of water, produces acetylene gas, which is really, really flammable. They use this in welding. So if you ever see people welding metal, acetylene is used for that because it can get really, really high temperatures. So I've got some water inside of the pumpkin, and I've got the pieces cut out. And then I'm going to put some of this calcium carbide in there. I'm going to pull the back out, and I'm going to light it.
Ow! Let me see the water.
Well, it's in there. You
Watch
can't
my
see the
phone
water.
die. It's on 1%.
I'll send it to you.
Okay.
Just in case it hits me in the face.
It's gonna hit your phone and break. That's why she's got a water box on there. Those are some big headphones. He can't hear me.
She's going to shoot straight to the water.
Okay, so like a little person in the face.
What if you
We didn't have enough calcium carbide.
Oh.
I'm trying a little more.
Why do you have a...
So that's the problem. The flame outage. You got to get the mixture. Marley, quit recording.
Marley, quit vlogging.
No, don't leave them in there. I'm going to try to get next year.
Hey, Brandon.
Can you not hear me that well?
That's rough.
Well, the pumpkin is so large that it's requiring a lot of the gas too. And my lighter is not, see how it's not lighting right away? That's the issue. Because when you stick it in there, you want it to be a flame right away.
Why don't you just like...
Get a stick as a match on it.
Yeah, but it goes out by the time you stick it in there. It's real, it can shoot out. You really want it to be, what I'll do next time is I'll pick the flame up and go like that. So there's a lot of variables you can do. So you have goggles on, and you start mixing things. Goggles like Claire, Summer, Wonderfulness. Alright. Now remember, you're supposed to be using an 8 by 8 centimeter. Did you put 8 by 8 centimeter piece of aluminum in there? Yeah, so you're going to measure your initial temperature, write that down, and then you go for the next step. Yeah, well, when it cools, put the salt in the trash, pour up the liquid in the sink. Make sure you have goggles on. No, they don't. You gotta have double protection. Kind of see that instantaneous reactivity of the aluminum. Chlorine.
I'm not directly above it. Love that.
Your GoPro's gonna get like dirty.
That's alright. Calcium carbide, and you put it in the presence of water, it makes acetylene gas. So that's been what we've been having like most of the day. It's just been flaming out. You gotta be careful because it can burn you. Now don't kick the pieces. We need. As far as the aluminum when it reacts with it, it's really pretty cool. Make sure you have goggles on over here. Xavier, goggles. I'll send you back over there to the Southern with your Trojan sweatshirt on. The Southern Trojans. Really? Your parents go to Southern? You went to Southern?
Okay, it's a long story. My grandparents are Notre Dame fans, so my dad wants to be the outlaw, so he picked the team that rivals with them.
Oh, okay.
And me's there.
Is that San Francisco Trojans?
USC,
Oh,
University
okay.
of Southern California.
And then the last
Nice
one.
reaction happening here. Autumn, I'm so proud of you. Goggles on. This is gunpowder. Now gunpowder has three parts. It's got the carbon part, the sulfur, and the potassium nitrate. And the potassium nitrate, as you can see over here, KNO3, what is it carrying?
What is it carrying?
Yeah. Oxygen, yes, that's the part that makes gunpowder very flammable. It's carrying 75% oxygen. That's why it's very flammable. And then it's got about 15% sulfur, which increases the temperature, and then there's about 10% carbon. Now, DuPont Manual, he made his money off of choosing the right carbon. That is, choosing the right tree. If you use a pine tree to make charcoal, that is, you heat the wood, it's not a good wood for gunpowder. He found that the willow tree worked the best, and his gunpowder was the most, I guess you'd say, active. So this is an example of gunpowder.
Is it gonna go off like immediately?
What?
Is it gonna happen immediately?
Maybe.
Oh.
Whoa! This is gunpowder.
That was cool.
Now this right here is what we've been working on all day to try to get nice explosion.
Smoke shop. Oh. Yo. Uh-oh, there it goes.
So it's just it's flaming out. It's not really doing what I wanted it to do. I don't know if the pumpkin's so big, but it is what it is. Let's try it again. Yeah, it's
allowable orbit to the
Hey, watching y'all.
Therefore, it can emit or absorb only certain amounts of energy corresponding to energy difference between two orbits.
Okay, so in the book on page 149, we want you to draw this diagram. This really shows you how the electrons are moving around the nucleus. They used to say in school that it was like a planetary model, that the electrons just orbited in direct paths, but they don't. They move in waves. So we want you to see a visual of what this looks like. On page 149, just draw these three different diagrams. Figure 5.13. You can see how it's going in a wave around the nucleus. The velocity and position of a particle at the same time. Whenever you measure something, you do what? You change it. Yes, so write that down. Whenever you measure something, you change it, and this is the reason why it's hard to know both at the same time. As you're measuring something, you're changing something else, that affects the knowing of both at the same time. Okay, that's a very important thing to note, that the quantum mechanical model makes no attempt to describe the electron's path around the nucleus. Write that down. And we just drew over here that the electron moves in a wave around the nucleus, but it's pretty technical when we start getting different shapes, like you see up here. When we look at the P shape, we're saying that the electron is going to follow this particular shape. That is, the wave is going to follow that shape. And we start trying to draw all those particular paths, it's going to create an atom that's difficult to visualize. So they don't do that. But the breakthrough was when Schrödinger stated that the electron moves in a wave nature around the nucleus. That was a pretty big change in how they used to think as far as the planetary model. And there's a lot of evidence for this. We talked about how alternating current and direct current shows that electrons do move in waves. So there's a lot of evidence for electrons moving in waves. The valence electrons associated with what? Yeah, the ones that are on the outer shell, like your coat, like what you're wearing. We can, understand a little bit about you by what you wear. Like you have a Kentucky shirt on. Aiden over there, he's probably hoping UK wins against Georgia. First SEC championship ever. I just hope they don't burn the city down if they win. So that's the valence. And how can you define the element that you're looking at? Will, how do you define the elements you're looking at? The last one. Remember, the last one tells you what you're working with. Now, I said element, right? If it's an ion, we'll talk more about that later. But if it's an element, it's the last one. Because remember, these things want to gain or lose electrons. They'd have to tell you more if it was an ion. They have to tell you the charge.